All right, I think we'll get started. So I'd like to welcome everyone to the Moberg Analytics webinar series on AI and neurocritical care. Thanks for joining us. So the question is, why are we doing this webinar series? As most of you know, in my past life, a bunch of us developed a CNS monitor that collected data from multiple devices, time synchronized it, and it allowed you to look at the brain as a collection of physiological waveforms. So what we've done in this next company is we're sending that to the web, and we're adding contextual data, images, labs, medications, and other information, and we're harmonizing that, and it becomes a platform for AI and machine learning. The goal is to further understand brain injury and to provide a tool that could allow you to better manage patients. But that's a big goal. And so we know we can't do that as a small company. And so we're building tools to help you do that. The first two things I want to talk about is this webinar series. So we're doing that to help you get up to speed in particularly in neurocritical care, machine learning, and AI. So the webinar series will be some tutorials, it'll be some cases and examples, and we hope to provide a data set and tools like Jupyter notebooks for you to use to follow along with examples. So that's the webinar series. If you have examples that you want to share as a webinar, please let us know. And if you have advice or ideas, also please let us know about that. A new thing we're thinking of starting in next year are these starter grants, and these will be small grants from us of cloud time, tools, and guidance to help you get a project off the ground. We're hoping to start these in 2024, and we'll announce it in the Neuroscience Monitor, which is our newsletter that I hope all of you are getting at this point. So this is how to connect with us. I would imagine all of you know how. I would urge you to make sure you subscribe to our newsletter. So a few housekeeping rules. This is a Zoom meeting. It's not on their webinar platform, but we will be moving to that for the next session. So we'll automatically move your names over. So it's a webinar. Please remain on mute until our QA session at the end of the talk. And to post questions, go to the Zoom chat feature located in the Zoom menu, and you can direct your questions either to everyone or to Craig Maddox, who will be the moderator of the Q&A session. The webinar is being recorded, and we'll make it available via our website after it's over. So today's speaker is actually a very special person for both me and the company. Ed came to work for me in my last company right out of college at University of Pennsylvania. He was an amazing employee, was there for about 2 years, and then he went on to get a graduate degree. We lost touch, and when I was hiring a student intern about 3 years ago, they had this person as a resume, as a reference named Ed Kim. And I said, wow, who's that? Called him up, and sure enough, there was Ed, who used to work for me. So in the last 3 years, we've developed a wonderful relationship. He's right here near us at Drexel University, and we've done a lot of collaborating with Ed and his team and many of his graduate students. So it's really a pleasure, and it's an honor that he's our first speaker in this series. Ed, his research interests are in computer vision, deep learning, neuromorphic systems that I had to ask him what those were. And it's actually using neurons and the way the brain works to mimic those for AI architectures. He's also does a lot in multimodal machine learning. Recently, he got an NSF Career Award for his work in neuro-inspired machine learning. And in 2021, DARPA funded him to explore sparse efficient coding for ultrasound images. And one of his projects is actually looking at ultrasound and looking at optic nerve sheath diameters as a surrogate for intracranial pressure assessment. I'm sure many of you are familiar with that technique, and Ed's group is trying to automate that through image analysis. So I really can't think of a better person to kick off our series in AI and machine learning and neurocritical care than Ed. So with that, I'm going to stop sharing and we'll turn it over to Ed.
All right, thank you, Dick. Give me one sec. Let me just turn on my video here. Okay, great. And let me see if I can share my screen, share content. All right, great. That works. And let's go to PowerPoint. Oops. Okay, great. Thank you, Dick, for the introduction. And it's good to reminisce going down memory lane. I really enjoyed my time there at Moberg Research. And yeah, and again, like I echo the sentiment that it's just a pleasure to work with you and Moberg Analytics again. So what I wanted to do was give you guys a brief introduction into some of the techniques, some of the representations, and what we're doing now in AI and machine learning, especially sort of looking at lots of multimodal data, enormous amounts of data that's being collected for patients and for patient care, and see what we can do with that data. And I wanted to first start off just saying, like, I think AI has become very pervasive in sort of consumer technology these days. Things like the chatbots, ChatGPT, for example, autonomous vehicles. It's using lots of AI these days just to do object recognition and detection. Things like reinforcement learning is being used in gameplay, right? So I think AlphaGo just recently, maybe a few years ago, outperformed the human in the top performing human in the game of Go. Of course, medical imaging, waveform analysis, and that sort of thing. And so I think we're hearing a lot about the successes of AI and machine learning and deep learning and all these new sort of technologies. And as Dick mentioned, I work at the intersection of AI and neuroscience. And really, I think for the first webinar, or maybe even series of videos here, what I wanted to do is really get us all sort of on the same page. So when we go into some more detailed deep dives into some of the coding and stuff, at least like we understand, we're on the same page with terminology, we understand what each other is talking about, we're on common ground. Okay, so so if you are sort of an expert in AI machine learning, I think maybe this would be more review, but I hope there's some nuggets of information that you can glean out of this. Okay, so here I wanted to start with just a first definition, right? Because I think we hear a lot of terminology like AI, and then we hear machine learning and deep learning, and really, like, what is the difference between them? I would say, like, functionally though, these days when people say AI, really they're talking about machine learning. And when they say machine learning or AI, they're really probably only talking about the dominant architecture and methodology in AI, which is like deep learning. And then within deep learning, there's all these like subsets of different techniques and architectures. And so really, I think these days, when we say any of these words, we're essentially all saying the same thing. But technically, there are some differences, and I do want to sort of highlight them in this graph here. So when we say like AI, here it's a definition here is a program, and I'm going to try to write here, see if it comes out. A program that can sense, reason, act, and adapt. And so really, like, at the at the core, at the base of AI, it's really just like this one core building block that you can imagine. I like to sort of equate this to thermostats, right? Thermostats back in the day, back, before the smart thermostat, just the one on the wall that you would sort of move around. You twist the ring to a certain temperature. And so why do I think that's like a basic AI? Well, if you think about it, that thermostat, it can do some sort of sensing, right? It knows the temperature in the environment. And then the human, the engineer who created that thing, embedded within it some way of reasoning, right? So think about like, it has some sort of like condition, right? We'll call this conditional. If the temperature goes above, I don't know, 72 degrees, then what are we're gonna act. We're gonna do some sort of action here. We're gonna cool, right? Cool. If the temperature goes below, I don't know, 67 degrees, then we're gonna heat, right? So we have this ability right here to sense, reason, and act on the environment. And so I would say that's sort of a basic AI, and maybe adaptation is sort of missing here. But really, then, see, I have, so if you go to the AI ML Reddit, you'll see that, everything behind AI, it's, pull off the shroud, it's essentially just if-else statements. Okay, so what is machine learning then? If we think about machine learning, we're going to say algorithms whose performance improves as they're exposed to more data. So what does that really mean? All that means is that there was a parameter, right? There was a parameter in this AI system, and that parameter was at like 72 degrees or that 67 degrees, right? Like somebody set that, like a human set that and said, okay, if something goes beyond this setting, this parameter, then I'm going to do some actions. And machine learning says that, well, where did you get that? Where did you get the parameter? And in sort of the old days, we would say, oh, those were like expert systems, right? So the human comes in and says, I know what the perfect temperature is. In fact, there's a slide back from the 1918, right? That says, oh, like the best temperature would be that 72 degrees with a humidity of 20%. Okay, so someone comes in and said, that's the parameter that should be set. Whereas machine learning says, well, why don't we learn these parameters from the data itself? So we have lots of data. We have lots of trials of this person coming in and setting the temperature. And as they set the temperature day after day, I can record it. I can say, oh, 71, 72, 73, right? And over time, then I can get a sense of what is the ideal parameter personalized for that person. And then I can adjust the model, the AI model, to act in that way. And so in that way, machine learning really is, can I learn the parameters from the data itself, not rely on a human to tell me what the important parameters are? Okay, so that was a big transition from sort of traditional AI to machine learning. And then really there's only one sort of dominant architecture, which, to the chagrin of some people, but essentially like deep learning has sort of taken over almost all of machine learning. And really deep learning is nothing more, I would say, like nothing more than just a way of thinking and visualizing how to learn these parameters in something called a neural network architecture. And I'll go into some of these neural networks and that sort of thing a little bit later. Okay, so let's frame the problem that we have. Essentially, like I mentioned before, just the amount of information that we're gathering, that we're collecting, is just exponentially rising, right? So we have tons of different types of data. We have categorical data, things like demographics, patient labs, treatment, medication, all of these things, all of these data points we're collecting. Not only that, we have these very different types of of data, right? We'll call this multimodal data. We have waveform data. Here's the Moberg monitor, CNS monitor, which back in 2003, 2006, I think I was working on some of the displays here, but we have these waveform datas at very high frequencies, right? So some of these are collected at 120 hertz. So we have lots of numerical waveform data. We have image data as well. We have MRI, ultrasound, CT scans, different types of image data. This goes to another dimension, right? Waveform, we have the one-dimensional signals. Image data, we have 2 or 3-dimensional signals. So we're talking massive amounts of pixel information, and I think if I remember it correctly, like DICOM format, image format is not compressed. So we're in the gigabytes, terabytes of image data. And then even more cryptic is we have this language data now, and the these large language models are doing very well with interpreting and understanding a lot of this unstructured data, such as doctor's notes. And so how do we take all of this data and do something with it, right? So maybe to sort of frame this into a very simple question, I think classification is probably one of the core objectives in machine learning AI. And really, what you're trying to do is you're going to try to take this input data, whatever this input data is, we'll call it the features of our data. We're trying to take the input and we're trying to bin it into certain categories, right? So we might be trying to bin it into like, this is a normal patient, or versus, this patient we need to do immediate treatment on, right? So there's like this sort of binning process that we're trying to do, and we're going to put in all of this feature data, and then hopefully the model will then learn how to correctly output that classification. So I'm going to switch here to a simpler example, and then we'll come back to more medical data. So in this case, what we have is a salmon and a sea bass. And really what we're trying to do, again, classification, we're trying to bin a fish, an unknown fish, we catch it and we say, is this a salmon or a sea bass? And if you look at this, you might get some hints, right? So if you're not you don't know your fish, like I don't know my fish, but I think the bottom one is salmon, the top one is sea bass. And so you might say, just by looking at this one example, you might say something like, oh, looks like salmon are smaller, right? So I might, here's an input to my model, to a feature of my model. I say, okay, let's measure it and say, if the fish that I catch, this new fish, is 16 inches or less, then I'm going to bin it into the salmon category. And this particular example came from the book, Pattern Classification. And really what we're saying is, I am the expert, right? I know the difference between salmon and sea bass. I know that length is something that I can use. And I'm coming up with that number 16, right? So where did that number 16 come from? It came from me. I'm the expert. So this is an expert system. And then here, this is what's called a histogram. So basically what I do is I start to collect data now, right? So I start catching fish and I say, this is a salmon, this is sea bass. And here, for example, what you see, like at this point, what you're seeing is the count of the fish that I caught at this particular length. So at 20 inches, if I look here, I've caught about 9 salmon, and I've caught about 23 sea bass. Okay, that's what this histogram is showing us. And then so now I'm thinking, okay, that 16 that I picked is right here. Is that the best parameter of the system? And so in the machine learning sense, I can say, well, why don't I learn that parameter from the data? And so what I can do is I can sample every inch, right? I say, okay, I'm going to make that separation at 25. how many do I get correct and how many do we get wrong? So if it's above 25, I'm going to say it's sea bass, and below it's salmon, right? So if I do that sort of calculation, I say, oh, that's terrible. That's a bad separation. So then I keep walking along, and what I find is that at some point, and I sample every single inch here on my ruler, and I say, okay, it seems that when I select 11 or 12, so maybe that's 11, well, maybe it's 12. When I select this parameter, then I have minimized the error. I have maximized my accuracy, minimized the error. And so by the data set that I've collected here, the best parameter, the best separator parameter is 12 inches. Okay, that's sort of like a intuition of how I might be able to come up with the parameter of the system. Okay, but we find that that's not great, right? It wasn't that it didn't separate the data that well. I got a lot of errors. And so maybe this one feature that I picked, this input, is poor, and I need another feature. I need another dimension. So then we can say, like, okay, let's look at the lightness, right? So the intensity of the scales of the fish, and this is a measure of the lightness. This is, again, the count that we have collected. And we can do this sort of exhaustive search of the parameter space to come up with the best parameter of lightness. But you can still see here that there is still some error, right? This is an error. This is an error. Okay. So maybe what we can do is combine features. So we have more and more features within the model, right? So I can have lightness on one axis, length on another, and basically what you do is you take this particular sea bass. So maybe this particular fish, it has a length of 20 and it had a lightness of like 7, and then you plot it on this. So 20 is up here, lightness is up here. So maybe this is where that particular fish would lie in this 2-dimensional space. And if you keep plotting all of these fish that you collect, you can see that now that I have 2 features, lightness and width, my separation is not a single point on, it's no longer like a single point on this dimension or this dimension. It actually becomes a line, right? It's a separating line in a 2-dimensional space. Okay, so now this is the only time that we're going to look at equations, but I think this one is one that you all are familiar with. You've probably seen this before. Just an equation of a line, right? Y equals mx plus b. That's like the slope intercept, which you can also just transform into the standard form of ax plus by equals c. And all this to say is that if I want to define a separating line, so this is our classification boundary, right? On one side, this is how we're binning sea bass and salmon. I can define it by this line, this equation of a line. And really what you want to think about is this x is the lightness and the y is the width. Oh, that's width. Okay, so it's some parameter a times this feature plus some parameter b times another feature. And let's say that now it's not just lightness and width, but it's something else. I have more parameter. I have more features that I want to put in, like the smell or something. I don't know. Like you have all of these features and you're putting it in. So then now I'm not in 2-dimensional space, I'm in 3-dimensional space, right? So and imagine it's like a room now. It's not just a flat piece of paper. And how do I separate a room? Well, to separate a room, I have to put a wall, right? And that's a plane. That's a 3-dimensional. It's a plane in 3-dimensional space, and that's how I'm going to separate. And how do I define a plane? Well, if this line was 2 and ax plus by equals c, a plane is just ax plus by plus cz. Okay, so I've added another feature, another dimension to the problem. And now we can come to this whole idea of enormous amounts of feature data, right? So I have lots of patient information. It's not just 3-dimensional, it's potentially 100-dimensional, 1,000-dimensional, right? Million-dimensional. And so how do I go from this to like a million-dimensional space? Well, I would be like ax plus by plus cz plus d. I don't know. I run out of alphabets. So traditionally, what we're going to do is we're going to drop the XYZ notation, and then we'll call it X1, X2, X3 to Xn, right? So now I can be in like million-dimensional space. And what do I have? I have these parameters, these weights that are going to define each one of these features. Okay, so now I'm in potentially million-dimensional space. Okay, so all that to say, this was just getting us in the frame of mind of like, how can I represent all of this information that I have? Well, I can have a big input space. I can have lots of features, and each one of those features is going to be weighted by some parameter. And that whole idea of this weight linear combination of features, that we don't like to write this notation out. It just takes too much space. And so generally what we're going to say is it's just this wx. It's a w vector times x vector. It's a dot product between the w and the x, and that's really that linear combination. And then we say, let's how can we visualize this so it's not so mathematical looking? We'll visualize it as each of the inputs as the circle, and we'll call these like nodes or neurons. We'll call these nodes and neurons. And each of the weights, how much are they influenced by? Each of them are going to be the edges of this graph, right? And so this graph of W1, X1 really is just W1 times X1, and then W2 times X2, W3 times X3, right? And you can just continue this pattern. And this is what we'll call a neural network. This is a neural network. It's a single layer neural network that represents that linear combination. Now, I think here it's actually really interesting to look at like biological networks, right? Because there's a very nice parallel between the artificial neural network and this is a pyramidal neuron within the brain. If you look at this pyramidal neuron, what happens is it has dendrites, because these dendrites are the inputs into the cell, and the cell, this pyramidal neuron, it's a cell. It has a cell membrane that surrounds it, and that membrane can hold a electrical potential. And as the inputs come into the dendrites, so it's actually a chemical process. It changes the membrane potential to a point, so it integrates all of the inputs until the point where it will passes some threshold, then it activates. It sends an action potential out from the axon to downstream neurons. And so this kind of idea is actually very similar to what we just saw, right? What we have are these inputs to a neuron. We'll call that neuron the cell body. And those inputs are just what? They're the input features that we just talked about, the X0, X1, modulated by the weights, by these W0, W1s, right? So we have this integral, this summation here of all of the inputs to the system. And then we have some output to downstream neurons. Now, there's one thing that also has a very nice parallel to to biological neurons. And that's the fact that there's like this action potential, right? There's a firing of that neuron. And really, what does that look like? Well, basically, the neuron is silent, so it has zero output. And then at some point, it fires, and then it's a binary, output of 1, really. So this is sort of the what we'll call the activation profile of a pyramidal biological neuron. And so we actually have that same sort of architecture within an artificial neuron, right? So we have this, instead of having this sort of step function that we see, we like to smooth this out, right? So we smooth it out, and so really it looks more like this, right, between a 0 and 1, and this is called a sigmoid function. So it really just squashes the integrated input between a value of 0 and 1. Okay, all that to say is that it's a very nice parallel to what a pyramidal neuron does. Okay, so we have this. Now we went from AI, machine learning, kind of, to deep learning, which is these neural networks. And now I want to bring it back, right? So here's the task, right? How do we want a binary decision here. Should this person go on cholesterol medication or something? And we have lots of different inputs to the system that we can consider. We can consider things like age, so it's one dimension, LDL, HDL. We have multiple dimensions now, 2-3 dimensions. Number of shrimp per day. It's the highest cholesterol food, I think, that I know of. So if you eat a lot of shrimp, that might be important to know. That's a feature. And then maybe, number of toes that you have. Does that actually play a part in whether or not I should be on cholesterol medication? I don't think so, right? And so if you think about this, then this problem, you might say, oh, your age, LDL, HDL, oh, these are really important features, right? So you might say the weights, if I were to just, as an expert, right, I might say, oh, let me set these weights to be pretty high. Like maybe age, I don't know, maybe that's like 0.5. LDL, HDL, oh, those are important. I'll put them like 1, right? Number of shrimp per day, I don't know, 0.3. That seems kind of relevant. Now I'm saying like number of toes, W5. I might say to myself, well, how do I indicate to the model as an expert that this doesn't really have any weight whatsoever? I would just say 0. I'd say 0. And what does that do? It does sort of this W5 times X5 is equal to 0, right? So if this weight is 0, it's going to essentially negate the effect of that input feature. Okay, so that's how I would do it if I were an expert, and I would come up with some value. 0 being no medication, 1 being medicate. Okay, or some you'd have to normalize, but essentially that's what I would do. And in machine learning, it says, wait a minute, maybe we can learn these weights, these parameters. Maybe we can learn these parameters from the data itself. And so what we can do is actually just what we can do is randomly set these weights just to completely random numbers, and then we just collect lots of data. We collect lots of data of people's age and their cholesterol and this sort of thing, and we put it through the model, right? So putting it, what we call a forward pass through the model, is essentially just this W1 X1 plus W2 X2 plus W3 X3, right? It's ... It's this linear combination of the input feature and the weights, and we get a result. And maybe the result of that is maybe the result of patient 1, maybe the result is like 0.2, right? And these are random weights, so this makes no sense. In fact, this person if a physician looked at them at the profile, they would say absolutely they need medication. So although your model says 0.2, it actually should be 1. It should be you should medicate. Okay, so now I have some error in this model, and I can then start tuning the weights. So here's a very simple way of thinking about tuning the weights. Think of like this model, this prediction gave me 0.2, but it should have been 1. So why don't I, instead of 0.5, I'm just going to go up. I'm going to go to 0.6 for the age parameter, pass it through the model. And if I put a 0.6, what happens? This goes to 0.15. And I say, oh, that actually made it worse, right? The error got bigger. I shouldn't have raised from 0.5 to 0.6. So maybe I'll just go down. So this is called hot and cold, or like basically perturbations of the weights. If I go down, now the output is 0.25. Then I come closer to what it should be, and I can say, oh, that's correct. I should sort of weigh that parameter down, and I do it for every single one of these weights. And you think about, there's only 5 here, but you can think I might have like 1 million of these, and I do it for every single one, and so I'm tweaking it as I go. This is very inefficient. There is something called gradient descent, or gradient, or derivatives of the objective function, which we might be going to later. But essentially, like, what the derivative tells us is which way to go. So instead of having to test up and down for every single parameter, if I can take the derivative of the objective function, it tells me exactly this one should go down, this one should go up, this one should go down, right? So I don't have to test them. I automatically know, and I can just sort of tweak each one of these weights accordingly. And this is very important, that I don't have to like tweak and test every single one. I can just do the gradient and find the direction for every single weight, because we don't deal with simple neural networks typically. We deal with these deep learning networks, right? So it's not just a single set of weights and parameters. It's it's weights 2, weights 3, weights 4, and potentially we have tens or hundreds of layers within these deep neural networks, and we have to find the weight. We have to find the tuning for every single one of these parameters. Okay, if you think about the number of parameters that we're dealing with now, think about like GPT-2. GPT-2, pretty sure, my memory, I think it's about 1 billion parameters. 1 billion, 1 billion of these weights, GPT-2. GPT-3 moved from 1 billion to 175 billion parameters. And they're saying GPT-4 is just 8 times that, I think. So it's like 1 trillion parameters. So that's how many of these weights that need to be tuned in something like a large language model. All right, so categorical data, I think, made a lot of sense. Very easy. You think like these are data points that we collect on the patient, their age, their demographics. We can say, are they on this medication? Yes or no. And so all of those things, I think we can visualize, right? We can visualize each one of those things becomes a feature input into a neural network that we can sort of tune the weights of and find out how much they contribute to the final goal. In this case, it was classification. And we talk about waveform data. Traditionally, waveform data it's very difficult to do. It's not traditional. It is very difficult to deal with because, potentially for 1 second of data, we might have, 1 second of data, we might have like 120 hertz. We have 120 numbers, potentially multiple different channels, right? So this network becomes very big very quickly. Lots of, we have temporal data, how do we deal with this? And so traditionally, I think maybe the easiest way is to think, well, can I somehow transform the waveform data into like summary statistics or some sort of categorical data so I can fit it back into this model of like, oh, heart rate variability, I can get a single number. I can get a single number for that and put it in there, right? So that's my feature one. I can be like, I don't know, presence of, or, PR interval, what's that? I put that a single number into there, or I might do like things like the average of these things, or, maybe even look at the variance and that sort of thing, right? So this idea of, it's also like dimensionality reduction, right? I don't want to deal with 120 hertz of data. Can I somehow describe it? And as a physician, I mean, this is what you're doing when you interpret. You interpret this information. You're looking at it. You're saying, what is important for me to pick out of this waveform data? How can I? Well, in your brain, you come up with a plan of action or a classification, but for the computer, it's like, well, how can I describe then to the computer what is going on in this waveform? What is important? And this comes back to this whole idea of expert systems, which, it has its place. Obviously, physicians, they know what's important to look at. You don't need to look at everything. Just look at this. But how can I best describe it to the computer so it knows to look at what I'm looking at when making these decisions? And this is the tricky part. This is really the tricky part about handcrafting or feature engineering your own features for the machine. This is it's called Ancom's quartet. I don't know if you're familiar with this, but essentially all four of these data plots have the same summary statistics. They have the same mean, variance, correlation coefficients, and they look very, very different. And I think this is the trouble when we do this sort of handcrafted dimensionality reduction of the data. Really, it's almost impossible to describe it in a way that fully captures what's happening in that waveform. And so, yes, summary statistics work well. That you should definitely look at how to extract data, how to extract features from the data. But I think these days, a lot of what's happening is we're letting the machine, instead of telling the machine what's important, we're letting the machine learn from the data, learn what's important. Okay, so we can mathematically capture the same intuition. And the first way really is this idea of the Fourier series. Okay, so I mean, this goes back to, I don't know, the 1800s, right, with Fourier. Essentially what Fourier says, oops, this is just a tone. What Fourier says is that you have any waveform, right? So this is a combination of different waveforms, and I think this one here sounds as conjunction. Fourier says we can approximate any waveform, any function, by a combination of sines and cosines of increasingly high frequency. So what does that mean? I'm not going to go into I lied. I said there was only one equation, but there's more equations, but it doesn't matter. Like I'm going to skip over the equations, and all I want you to notice is that we have cosines and we have sines, right? And we have some contribution of that sine and that cosine to the overall reconstruction of that waveform. So basically what happens is here I have that waveform and I want to reconstruct, I want to express mathematically to the machine, how can I describe this to you without using summary statistics? And I say, okay, use this much of this waveform plus this much of this waveform right? So these are increasing frequencies of waveform, and I'm adding them all together. And eventually, if I add up enough of them, I can then almost exactly approximate this this waveform. Okay, all that to say is that now I have a way of mathematically representing, and I know I'm running into the Q&A, but I just have a few more things to say. I'm mathematically representing the waveform, right? So I don't need to use summary statistics. I can use coefficients of increasing basis sine and cosine functions. I can use wavelets. Wavelets are another type of basis, but it's both temporal and spatial. I can describe a waveform using coefficients of wavelets, or I can begin to then say, all right, let me not even define what the basis is. I'll let the machine learn the basis itself. And so things like principal component analysis, which is a transform basis, things like autoencoders, we'll dive into some of this later on, and things like sparse coding. All of these things say, again, I'm not handcrafting anything anymore. I'm letting the machine learn the coefficients and even the basis on which those coefficients are multiplying. I can learn all of that from the data, and that's really where things have been moving on. Okay, so I know I'm running out of time, but high level, what we were looking at is we have lots of multimodal data, right? We had the categorical data, we had the waveform data, and how do we represent that information? And we also have image and language data, which I hope that we'll have time later on to dive in and see how those are represented. And then we can build sort of these complex models on top of them to do interesting things. Okay. So I don't know, Craig, should I pause here for questions, or?
Yeah, sure. It's probably a good time. I know this is a lot.
Yeah.
But yeah, so if you have questions, I mean, we're pretty small, we're a manageable group here. So if you just want to come off mute and ask the question, alternatively, you can put it in the meeting chat directed to either everyone or directly to me, and I can relay it to Ed. I just want to, while you guys are thinking and queuing up questions, I just wanted to thank Ed for bringing his expertise. It's really cool to listen and to hear lectures from people who have such a great understanding of kind of this intersection, right? It's really cool, at least for me. That's fascinating.
I have one question. This is Fred Bowman. To what extent have these models been pushed, and which of the feature parameters are coming out with the strongest weighting?
Yeah, so those are great questions. The first one is like, how far have they been pushed? And I think they're really being they're really being tested right at the bounds of computation and memory, not so much like the bounds of like information, I would say. Because like if you look at like GPT-4, which is probably the largest, GPT-4 is probably the largest model in existence with 1 trillion parameters. That took, they estimate that took anywhere between $100 million to $200 million to train, in terms of like computation time, hardware, data collection, and that sort of thing. And Right. I mean, data has a lot to do with it, right? It's able to scrape terabytes, even more, exabytes of data from the internet. So I would say, like, yeah, they're being pushed to the limits where really only a handful of companies in the world have the resources to do something like this, right? Like Meta, OpenAI, Google, Amazon. That's about it. So I think the limits are, I don't know, maybe computational and financial at the moment. And then in terms of the weighting and importance, I think that's a really important question, because as I was able to explain in a simple neural network, we can actually look at the weights and understand what's happening. But the problem really is that we're not dealing with simple neural networks these days. We're dealing with deep networks of trillions of parameters. And there's like non-linearities between each one of these layers or each one of these operations. And so at this point, even at this point, like 4 or 5 layer neural network, I have no idea what's happening, because the contribution that I see here goes through some, non-linearity, which then does some downstream, downstream effect, which, each one of these also has downstream effects. And so that's why a lot of people, in fact, everyone basically says these deep learning networks are black boxes, because it's become so big that it's uninterpretable as to what's happening. And really what the only faith you have is in gradient descent, telling you that if you wanted to change the output of this model a certain way, I can tell you how a trillion little knobs should be turned, but that's about it. I can't tell you the contribution anymore. So that's a big problem.
Yeah, it's interesting. It's in stark contrast with the proof demanded for proving and for retesting and confirming questions in the medical field that the group on the phone is going to do. Very, very interesting. I had one question come up in the chat. So you talked about waveforms and how we can use Fourier to on those. Can you give a simple description of what's used for images, or might we get into that next time? Or
you can get into that next time. Okay. But it's essentially it's almost the same idea, where you can think of like wavelets or two-dimensional basis functions in two-dimensional space, right? So like a wavelet kind of look like this in 1 dimension. In 2 dimensions, it looks like, I don't know how to draw it, but it looks like this. It looks like edges almost, right? And you have like edges that go this way, edges that go that way. So these are handcrafted wavelet type, and in fact, JPEG compression uses wavelet basis for its compression techniques. Again, we've used these basis functions, and then we realized that we can actually learn these basis functions from these basis patches, essentially from the data itself. And so that's where you see like these what are called convolutional neural networks that are basically blocks of weights. These are two-dimensional blocks of weights that are strided over the input image. And through the process of gradient descent and learning, we actually can learn what is the appropriate generator of the image data. And in fact, if you look at like what a wavelet looks like, and you look at what's learned from these convolutional neural nets, it's pretty similar. So you sort of got the expert got it right in some sense, but you can learn many more convolutional, these filter elements from the data itself, and just relying on handcrafted wavelets.
I'm glad there are Python libraries and things like that to handle this math for me, because it is way over my head. So I guess that's what's cool about some of the modern tools, being able to handle this stuff for you. Yeah, you gotta, once you gain an understanding for the type of algorithm that solves a certain type of problem, you don't have to worry so much about the math, which is which is a boon for me because didn't do so well. Cool. All right. Well, last chance for.
This would be again, Ed. It sounds like you have good job security.
Yeah. On one hand, right, there's just like, right, innovation is on an exponential clock, right? Things that I read a couple days ago are sometimes obsolete. But on the other hand, right, like ChatGPT is an incredible programmer, I'd say. So, on one hand, yeah, I think so. But on the other hand, there definitely is going to be displacement with the capabilities of these AI systems.
Mm-hmm. Thank you.
Sure. Yeah, just in closing, I think being in the medical field and the stuff that I work on, a lot of times it doesn't have the same impact that it would have if you're like dealing with humans and decision making in critical situations. So I think like the combination of medicine plus AI is really admirable and impactful. So I'm glad to see you all attending and here, and I hope that I can play a small piece of helping you get to your goals as well. So yeah.
Well, Ed, thank you so much. We really appreciate that introduction. And you'll be doing the next one, and we'll take what you've done here and take it to another level. I would urge all those who are listening to this to send us your comments. As you know, this is our first one. We want to make sure this meets your needs. So please send us feedback. We can tailor this pretty much however you want. So the best way to get feedback is to craig@moberganalytics.com. And thank you. And I'd also like to send a special thanks to those of you who are in the UK and Europe who are spending their Friday evening with us. So thank you very much. And we will let you know the date of the next webinar in our newsletter and on our website. So please check that out. Again, thanks, Ed, and thanks to all of our attendees.
Right. Thank you all.